Hello, I am Sang-Yong Park from Technical University of Berlin. I'm leading the group of smart mobility systems here. And today I will present this work exploring planning and operations design space for EV charging stations. This is a joint work with my former colleague, Dr. Alma Pripstil, Professor Wanli Chang, Professor Anuradha Anaswamy, and Professor Samarjit Chakraborty. Motivations for performing EV charging research is as follows. Electric vehicles suffer from short drive range and long charging times. Level 1 charging is typically considered to take hours, up to 10 hours, and level 2 charging would take about 1 or 2 hours until the batteries are fully charged. And fast DC charging, even these usually take more than 20 minutes, and the drive range of the recent electric vehicles are typically around 300 to 400 kilometers. These pose as an inconvenience to the electric vehicle owners these days. And lack of EV charging infrastructure limits a wide adoption of electric vehicles. And most of the electric vehicles are used for commuting as a second car. There are a number of EV charging architecture concepts. The first one is EV charged at home as a domestic appliance. And the second one is EV charged at home with separate electricity billing, potentially cheaper, supported by subsidies from the government. Third option is the public street parking with multiple, not location restricted charging service providers. You can find these sort of charging spots in the cities these days, and which are operated by a service provider. And the fourth option is the privately owned charging station offering public access, which is the target of this work. Public EV charging station looks like a gas station concept for EV charging. Charging station operator is motivated by the financial benefit and provides the charging service. They should be able to offer a differentiated service, for example, fast DC charging, to encourage the customers come to their charging stations instead of charging their vehicles at home. And it is often combined with the renewable energy, as you can see from the figure on the right. It's a Tesla supercharger station, and on the roof there exists a photovoltaic panel array which would also power the vehicles with clean energy. There are a couple of agents considered in this setup. The first one is, of course, the distribution system operator, who owns and operates the grid, and it's fully regulated in many countries. There are suppliers or market, which interfaces between distribution system operator and the customers. In this case, the charging station operator. Charging station operator buys electricity from DSO or the electricity suppliers and sells their service to electric vehicle owners. This concept is not widely adopted yet, but we believe that it has certain strengths. It provides better charging services that could not be obtained at home or parking areas. At home, impossible due to the high cost of the chargers. And in parking areas, people just like to park and leave their vehicle for hours, which makes the setup not so viable. And this architecture has strengths in allowing specialized investment on high capacity equipment, battery storage, and renewable energy sources. It also enables more flexible use of electric vehicles other than commuting. If you have these stations, you could let the vehicle be charged for 20 minutes and then continue your travel afterwards. There are hurdles as well. They should be able to provide differentiated service compared with home charging or other public charging services such as chargers at parking spots, while being economically beneficial in order to be feasible. The target architecture we consider looks like the follows. It's a public EV charging station equipped with PV panels and an energy storage. So the grid connection guarantees availability of the electricity at all times, while the PV panels ensure reduced carbon emission and electricity bill reduction from the charging station operator side. There's an energy storage system which relieves renewable energy generation fluctuation. So when the solar power is not available, this is going to supply the vehicle's charging power from itself. And it exploits electricity price fluctuation when there is a price difference according to the changing time. And it also comprises fast DC charging posts and, of course, the vehicles who come to charge their batteries. First, I will state the first problem of charging station operation. The objective is to maximize the charging station net income over an infinite time window. The control variables are energy storage system, ESS charging and discharging currents. And we synthesize a controller which determines when and how to buy grid electricity and from which source, either the grid, the photovoltaic array, or the energy storage system to charge the electric vehicles. The solution methodology is explained here. We use stochastic dynamic programming approach based on Markov decision process modeling. We take stochastic models of cloud coverage at a certain location and EV arrival rate over time. Using this stochastic information, we build transition probability matrix of this MDP model and also the transition reward matrix, basically about the financial gain the station operator could have. We solve the MDP optimization problem using relative value iteration method, and we try to maximize the average reward over a long period of time, meaning that we want to maximize the financial benefit. And as a result of this, a controller will be synthesized with an optimal policy, and we evaluate the actual return on investment using an actual EV arrival and solar irradiance profile. This process is summarized in the figure below. From now on, I will explain the models which are used to build this Markov decision process model of the charging station. For solar irradiance of the charging, which arrives at the photovoltaic panels in these charging station, we build a transition probability matrix of cloud coverage over time. The cloud coverage is classified into 9 levels, ranging from 0, which denotes no cloud situation, to 8, a full cloud situation. And the probability matrix is calculated using measured value from Munich. In the matrix below A, the rows denote the current cloud coverage level, and then the columns denote the next cloud coverage levels in the next time slot, and the values denote the probability in percentage, how much it's likely to change from one cloud level to another cloud level. Such a probability model is combined with the global solar irradiance model shown as in the equation above, which takes into account longitudinal and latitude information of the geographic location of the charging station in order to calculate the solar irradiance in the end. As for electric vehicle arrival and service model, we use a model which follows Poisson distribution, where the average arrival rate is changing over the time of day, as shown in the bottom left figure on this slide. You can see that the charging demand peaks at around 8 o'clock in the morning and slightly after 6 o'clock in the evening, where there are many vehicles on the road. And the EV charging service is modeled as an MMCK system in queuing theory, birth-death system. And the initial state of charge of arriving EV batteries should also be assumed, because this determines the amount of time they spend on this charging station. And it's taken from a work which has modeled the battery charging demands. The electric vehicles arrive at the charging station usually with the SOC between 20% and 40%. For the grid electricity price, we assumed time of use pricing, where the unit electricity price changes according to the time of day. We assumed three different rates over a day, and they have a high peak period, low peak period, and the base period, where the costs differ. And we've taken the values from Los Angeles Department of Water and Power for our evaluation. For the battery and the PV panels, we used a widely used equivalent circuit models, which are shown in the figures below. So for the PV, we use one diode model, and for the battery, we use the widely used second order equivalent circuit model. Based on all the component models I've described until now, we build a charging station model as MDP. And we consider discrete state of charge steps for the batteries and cloud coverage level 0 to 8, as I've described already. And we assume the number of cars in charging station to be between 0 and a certain maximum number. And we also consider different time of day to comprise a state in MDP. We discretize the time slots and model it as different states. And all these are combined to construct the state in the Markov decision process model, as shown in the figure below. And there are the transition probability matrix and transition reward matrices, which are associated with the state transitions in the Markov decision process model. After we've built this Markov decision process and the transition matrices, we apply a relative value iteration method to get the to find the policy which would maximize the average reward over a long term. And the average reward is the long-term net income, and this algorithm finds the optimal policy, which is basically a vector of actions for its corresponding system state. And when the system state is given for a certain time slot, then the controller is able to output the control output. The simulation framework is as follows, and this is implemented on MATLAB with the models and all the solution methods, the control policies implemented. And we use discrete time simulation and takes EV arrival and cloud coverage data from other work or the measured data in Munich as an input. We use the synthesized controller to finally evaluate the return on investment of the components which are there in the EV charging station. Based on the charging station operation problem, which I described until now, I will briefly describe the charging station planning problem. The synthesized controller from the charging station operation problem outputs the control policy for specific sizes of photovoltaic arrays, energy storage systems, and the number of chargers and charging speeds. However, in order to explore the charging station planning problem, we should play around with the different sizes of batteries, PVs, and so on. So we now consider the charging station operation problem as a subroutine in this charging station planning problem, and regard the charging station operation problem as a constrained single objective problem, which maximizes the profit per day. And we call this subroutine many times in this heuristic algorithm, which combines sequential quadratic programming and the greedy algorithm. For the sake of time, I won't go into the details in this presentation, but if you're interested, you could ask questions or contact us or read the details in the paper. This slide shows some results for 4 days of operation in Munich. And the upper left graph shows the power flow, power output from the photovoltaic panel, or power in and out of the battery, and the electricity draw from the grid, and the power which is supplied to the electric vehicles. So the synthesized policy works, and you can also see that how the battery is controlled over time to charge the batteries while maximizing the benefit for the charging station operator. And on the right hand side, you will see that there are traces of the charging station battery state of charge, which goes up and down according to the unit cost of the electricity which is available from the grid. And one more thing to note would be that if you look into the bottom right, you see that the vehicles are arriving more at a certain time of day, and most of them are served. But if they have come, but there are no chargers available, there might be cases that they will have to leave without getting served. Now we will look into depreciation analysis. The battery and PVs don't last forever, and they age. And the battery and PV installation costs are still significant when building such energy systems. Lithium-ion battery pack costs have come down quite significantly, and then they are considered to be $130 to $150 per kilowatt hour when talking about electric vehicle batteries. And for PV panels, they are also cheaper these days and cost about $1,300 to $2,000 depending on the application. But since the costs are quite significant and batteries can be used for several thousand cycles, and PV panels are considered to last 25 years or so, there is this question whether energy storage systems and PV installations are of benefit at all for the charging station operator in the long term. The figures below show how the batteries age, for example, and then depending on the patterns of usage, the number of cycles could vary quite a lot. Taking this into account, we have done the design space exploration in terms of the profit per day. If you look on the right-hand side graph, the z-axis is the profit per day in US dollars, and the two horizontal axes correspond to the size of the energy storage system and the size of the photovoltaic array. So you can see that there is a global maximum according to certain sizes of the battery storage and then the photovoltaic array. And our simulation framework allows us to perform such an analysis. We find that battery systems are hardly beneficial if the costs are above 500 US dollars per kilowatt hour, but also see that significant savings are possible if the current rate of falling prices continue. Yeah, and we have looked into, we have done design space exploration of public EV charging stations. Charging station operation problem is formulated as a Markov decision process and solved using relative value iteration algorithm. Charging station planning problem is also formulated to figure out the optimal sizes of components. And such architectures are predicted to be more profitable as the component prices continue to fall. Thank you for listening, and I'd welcome questions. Thank you very much.